So welcome back, and as ever in this third lockdown, I hope you and your family are well. So welcome to this next lesson on capacitors. Let's see if we can take our knowledge just a little bit further. So now what I want to look at is capacitor networks. And what I mean by that is similar to what we did with resistors, wiring them in series and parallel. Okay, and I'm going to do parallel first, which is interesting. That's usually the second one I do when we do resistors. Now, why would you ever want to do this? Okay, well, you want to do it to give students a rough time when they're answering exams. No. It's because if you can imagine in your toolbox, you might only have, here's a tray of them. You might have a whole load of capacitors, but they're all the same value. How do you get other capacitors that you might need when you're building an electronic circuit just using these? Okay. So you need to know how to wire them up so combinations of capacitors can produce different values from a single capacitor on its own. Okay. So let's start off with a parallel arrangement. So here's one capacitor. Here's the other one. And if we wire them in parallel, notice that the left-hand plate of the top one is connected to the left-hand plate of the bottom one, so must have the same potential on it. And on the right, the two right-hand plates are connected together, so they must have the same potential on them. Okay, even if the capacitor values are different, so let's make this C1 and C2, and we'll make this equal to 100 microfarads, and we'll make this one equal to 200 microfarads. You'll notice, by the way, we draw the capacitor plates always the same size. Get a bit clearer. Always the same size. We don't tend to change the size of the plates to represent the sizes of the capacitance. Okay, so what's the total capacitance of this circuit? Okay, wire it up to a battery. I'll bring it in from underneath because I'm not tall enough. So there it goes. Give it a few moments. It's all balanced out now. The current's zero. There's no charge moving. Remove the battery. Okay, and one side will be positive and one will be negative. So there'll be a voltage across these two terminals. Yep, but remember, the voltage across the bottom one will be the same as the voltage across the top one. So the first way to solving this is to say that the voltage is the same across both. Okay, so because they had the same battery across them, so they were at the same potential. Okay, so we use Q equals CV here. So let's have a look at how much charge is stored on the top capacitor. Okay, so Q1, Q equals CV, will be C1 V1, but I'm not going to write V1 because V1 is the same as V2, which was the same as the power supply. Okay, the charge stored on the bottom capacitor, well, twice the capacitance for the same voltage, so I'd expect Q2 to be twice as big. C2V. Okay, so what's the total charge stored? Okay, well, the total charge stored will be equal to Q1 plus Q2. Yeah, that seems fairly obvious. Okay, and if you look at that, the total charge stored will be C1V plus C2V. Okay, and then the final little twist here is the total charge stored, must be the total voltage, which is the same, and the total capacitance. So this Q becomes C total, Q equals CV total, okay, which is C1V plus C2V, okay, and then you can say, oh yeah, but look at that, okay, voltage on this side, voltage here, so the total capacitance, I'll write it in full now, C total is C1 plus C2. It's sort of obvious because you're adding the charges. Obviously, this goes on, for as many capacitors as you have. Yep. But there, how shall I do this? Put a ring around it. There is your formula for capacitors in parallel. Now, look very carefully. Okay, what you do is just add the capacitances. So C total here is just 300 microfarads. And can you see why I did this one first? Because it's the easy one to do. But what's more important is it is exactly the opposite, if I can say that, to resistors. Okay, resistors in parallel, you do not add them. Okay, do you remember it's a 1 over 1 over type thing? It's a reciprocal thing. Whereas capacitors in parallel, you do add them. Okay, so it's an easy one to do in exams. Can I just justify it? Yeah, I'm going to justify it very quickly. Okay, if I haven't done so already. For me, it's quite easy. What I imagine is just pushing that capacitor up a little bit and pulling that one down. And if you push them together, do you notice that instead of having plate area that big, with two of them, we've got twice the plate area, okay? Because we've got this bit of metal and that bit of metal. Twice the area to spread electrons onto, okay? So if you've got more area to put the electrons onto, you can put more electrons on for the same voltage. And do you remember capacitance tells you how much charge you can store per volt if it's in SI units. Okay, so the parallel one all seems really logical. Just add the capacitors and hint, if you want sort of memory hint, okay, capacitors in parallel, the total capacitance will always be bigger than the biggest. So if you start off with a 200 and you put a 100 in parallel with it, you'll always have more than 200 microfarads. So now let's look at capacitors in series, and this is a little bit more fiddly. So I've drawn a circuit there. It's pretty obvious what I've drawn. I've drawn two capacitors. They do not have to have the same value. They do not have to be in any particular order either in the circuit, but they're connected to a power supply. And if you remember, I'm going to try and stop saying this, you switch it on, you leave it for a few moments so everything balances out. Okay, so what's the total capacitance here? Well, I need to show you how you would work that out. So let's have a look at the voltage across the battery. So there's the voltage across the battery. And Kirchhoff's second law, yeah. So that voltage is going to spread itself across this capacitor and that one. So we'll say there's some voltage here, V1, and there's some voltage here, V2. So Kirchhoff's second law, let's sort of do that sort of properly. In a single loop of a circuit, the sum of the external PDs will be equal to the sum of the EMFs. Yeah, that's all good. Okay, so Kirchhoff's second law holds. So V of the battery is equal to V1 plus V2. Okay. Now, the next thing, which is really tricky, okay, is really tricky to explain, is, I'm going to try and justify it, but bear with me. And I don't find textbooks or other teachers justify this either. And I found this really weird when I first started learning this sort of stuff. Okay, those capacitors can be completely different values. Okay, but in this circuit in series, any capacitor in series with another one, regardless of its value, will store the same amount of charge. Okay, that is really quite weird. Okay, I'll give you one way of trying to justify that, but before I do, In some ways you don't need to know this, but I'd like to point it out because it is counterintuitive, yeah, that all values of capacitance in series store the same amount of charge. I didn't put the word amount in there, but you know, you get what I'm talking about. Okay. It's partly, this is not justification, it's partly to do with how the voltages sort of split across the capacitors. If you think about it, a bigger capacitor needs less voltage to store charge, so we'll have a lower voltage across it. And a lower capacitor needs more voltage to store charge, so it will have a higher voltage across it. That is not a justification, but that's sort of one way of sort of waffling my way through it. Okay, but I think this is a bit more helpful. Look at how the charge separates on this. So it's pretty clear that this plate will become positive, and it's equally clear that this will become negative. And here's the clever bit. Okay. Obviously, if that's positive, this plate will become negative. And the other capacitor's plate here will become positive. Okay. How do I justify that? Okay. There are electrons here. They repel electrons in this piece of metal because there's an electric field and push them that way. Okay. Another way of looking at it is, well, I suppose you could think about these electrons here, yeah, repelling electrons right the way across the system. But I think it's best just to say, you know, look at it from this point of view, that those electrons repel electrons from this plate, and there they end up. Okay, these electrons repel electrons from this plate, and off they go, and they kind of, it's a sort of circular argument, but you get my point. Okay, next thing that I find really interesting on this is, look at the charge on these plates. This plate and this plate are connected together and have the same charge on them. Okay, so what I'd like you to think about here is, this is not particularly good physics, but just kind of remove that. Okay, this is just one way of hand waving and trying to explain it. Because the charge on here is neutral overall, just remove it. Okay, and what you're seeing there, therefore, is this charge and that charge, if you remove the middle one. Okay, and if you do that, one way of looking at it is to say, well, okay, doesn't it sort of look like the two plates are further apart? It's not a brilliant justification, I must admit, but it's kind of a way I think about it to make sure I get it right. That this plate and that plate are much further apart than they would be. So the electric fields are like such that they wouldn't, if they were far apart, hold charge as well. So I'm expecting the capacitance to drop. Okay, now let's see if we can justify it mathematically. Okay, so we know that Q, the total Q on this system, okay, the total charge stored will be equal to CV. Okay, so the total charge on both of those added together will be the total capacitance, yeah, multiplied by the voltage of the battery. Okay, and maybe I'll put a little T there to remind us that those are the total values. This is really the EMF of the battery, isn't it? Okay. Right, so let's rearrange that. So V, the voltage of the battery, yeah, will be equal to the total charge divided by the total capacitance. Oh, that's interesting. The total capacitance is headed off down below the fraction. That's interesting. That's something to take into account. Okay. So, what is V1? Well, V1, yeah, because Q equals CV, V1 will be Q1 over C1. V2, Q equals CV, so V2 will be Q2 over C2. So we now have three expressions. Yeah, we have the total voltage, total charge and total capacitance. We have the voltage across one capacitor, and we have the voltage across the second capacitor, and we have values of those. And using Kirchhoff's second law, surely the total voltage, the total voltage, okay, will be QT upon CT, and the total voltage has to be these added up, okay, V1 plus V2. So Q1 over C1 plus Q2 over C2, and then you notice what happens here, okay. Take the charge out. Yeah, I'm just going to be a bit sort of mathematically lazy and sort of do this sort of thing. Okay, so what does that give us? It gives us 1 over the total capacitance is equal to 1 over the first capacitance plus 1 over the second capacitance plus ... 1 over Cn. Okay, I will just drop that in plus ... plus 1 over Cn. Okay, so I'll just put a red line around that lot. Okay, now those of you who are mathematically astute, which is most of you, will kind of go, well, yeah, okay, that's pretty obvious, FJ. But what I want to say is, and I know this is not quite true in maths, because you can put powers of -1 in and things like that. When you do your A-level, okay, can you consider there is no formula for the total capacitance of capacitors in series? Okay, just hear my voice there. There is no formula for the total of capacitors in series. There is, but go with this one. Okay, which means that if you hear my voice in the exam, you'll do all this maths, and then you won't write down that number as the answer. You remember that the formula you had doesn't give the total capacitance. It gives 1 over the total capacitance. Yeah, so it might give 1 million farads to the -1, and then you must remember to reciprocal that number and have 1 millionth of a farad, 1 microfarad. Okay, so just to end on this one, okay, compare with resistors. In other words, sort of bad physics, isn't it? But when you get resistors in series, you add them. When you get capacitors in series, you do not add them. You use the reciprocal formula, and you don't forget to tip your answer around right at the end. We've all done it. The reason you won't make that mistake is because I've told you in previous bits of the films that capacitance values are very low. So if you get a capacitance value that's very high, like 1 million farads, you cannot be right. Do you see what I mean? It's got to be wrong. And look at it again and go, oh, okay, I know what I've done wrong there. Okay. Just as a hint, compare with resistors. As you add resistors, okay, the more resistors you add in series, the greater the resistance. Okay. The more capacitors you add in series, the lower the capacitance. Okay, and I did that sort of lame thing by saying, imagine that the plates on our left and right are now further apart. Okay, so the more capacitors you put in series, the lower the capacitance. And one hint is the capacitance will always be lower than the lowest in the series chain that you've got. So let's quickly look at a complex network. You're kind of used to this sort of thing with resistors. We've got 4 capacitors here. At A level, they're typically the same numbers, but there can be any numbers you like, any values you like. Okay, how would you solve that one? How would you find the total capacitance? You should be good at this now. Look at it and go, well, let's get rid of these first. So push those two together. So add those two in parallel. And then you've got 1, 2, 3 in series. 1 over that one plus 1 over that one plus 1 over that one will equal 1 over C total. Then reciprocal it. Boom. You've done it. You've got the total capacitance. So let's put all this together and look at a quick example of capacitors. I'd like to do capacitors in series because that's the kind of tricky one. So let me quickly draw our circuit. Rather than draw it beforehand, it helps me to talk you through what I'm drawing. So here's one capacitor value. Don't know what it is yet. Here's another capacitor value. Not sure what that is yet. And let's go back to the battery. There we go. Okay, so let's put some meters on here. So I'll do it in a different colour just to make it clear that it's not really a circuit component. So let's look at the voltage across there and the voltage across there. I always think it's nice to draw circuits in front of students rather than throw the worksheet up, so you can sort of see how they're built up. Okay. And I'm not going to put a voltmeter across the battery, but you know that once this is turned on and left on for a while, V1 plus V2 will equal the voltage on the battery. Okay, and we'll put some component values on now. So we'll make this 50 microfarads. And it's quite typical to write it like that rather than 50 times 10 to the minus 6. Okay, and let's make this 100 microfarads. Okay, so let's see what we can do here. Well, firstly, and if you were to join my video a bit late, you'd think I've made a mistake and haven't. Switch on, leave it for a few moments, and we'll investigate that in a later video, for all the charges to sort their lives out and for the total voltage across these two to be equal to the total voltage of the battery or the EMF of the battery. And then if you want, you can disconnect the battery. You can flick the switch off. It doesn't make any difference. These guys remain charged because there's no circuit. They can't lose their charge. And if the dielectric is a perfect insulator, no charges can move across the gaps. Okay, so if you joined my video late now, you would have had to have seen that I've turned on, counted to 10, turned off. So you can get rid of the battery now. It's not relevant. These guys are now storing their charge. Okay. Well, something interesting will happen with the voltages, and I mentioned this a while ago. Let's make this a 12-volt battery, 12 joules per coulomb. Okay. Now, again, I didn't justify it very well, and it doesn't really come up in exams, but when you put capacitors in series, they always, regardless of value, store the same amount of charge. Okay, now knowing that, you'll look at this one, you go, right, okay, then if this one stores the same amount of charge as that one, and it's got half the capacitance, okay, it will need twice the voltage across it, okay? Because remember, capacitance is how much charge is stored per volt. So if it's got a low capacitance, it won't store much charge per volt, so it'll need a bigger voltage to have the same amount of charge on it as that one, okay? Now you can see the ratio here is 50 to 100, so it's 2 to 1. So this needs the bigger voltage, this needs the 2 lots of volts, and this needs the 1 lot of volts. So I think you're happy that that'll be 8 volts, and that will be 4 volts. Okay. Now, how much charge is stored in this circuit? Okay. Well, Q equals CV. So we can do for this one here, Q equals CV. And for this one, we can do Q equals CV. Okay, you can bash that out yourself, but it's not that hard. Okay, so C here, 50 microfarads times 8, so 400 microcoulombs is the charge stored there. And on this one, okay, the charge stored on this one is 4 times. Oh, well, why do I bother doing it? What have I taught you? Irrespective of value, the charge stored on both will be identical. Okay, 400 microcoulombs on each. So let's see if we can use the numbers that we've got to work out the total capacitance here. Well, if you think about it, we've got the total voltage. Yep. we've got the total charge, because we've got the charge on the first capacitor and the charge on the second capacitor, so we can look at the charge that's stored. So let's do that a little bit more mathematically. We know that Q total is equal to C total V total. So what's the total capacitance going to be? So the total capacitance is going to be, move the V over, Q total over V total. Okay. So let's see if we can put that together. Well, the total capacitance will be equal to the total charge stored divided by the supply voltage, the total voltage. So the total capacitance will be the total charge stored, in the whole system, okay? And we said that the charge on both is identical, okay? So the kind of charge stored in the system is 400 microcoulombs divided by 12. And if you work that out, you get 3.3 times 10 to the minus 5 farads, which is the same as, if you think about it, 33 microfarads, and that is the total capacitance. So if you were to do 1 over C1 plus 1 over C2 and then reciprocal it, you would get 33.3 recurring microfarads. Now, one or two of you might be a little bit confused by this, so I've got a tiny bit of sort of explaining to do just before we finish on this bit. We've got 400 microcoulombs on that capacitor and 400 microcoulombs on that capacitor. So you might say to yourself, well, why is the charge stored not 800 microcoulombs? Okay, I'm going to waffle my way through this by saying, do you remember that we separated charge on this plate and that plate? And we separated charge on this plate and that plate, okay? But the external circuit is connected to this plate only and that one, okay? So you can kind of forget what's happening in the middle. So the total charge stored is only 400 in total. I guess the effect of adding more capacitors in series is to kind of create more plates in the gap which don't serve a purpose. That's not a very good explanation, but you can sort of see why we haven't added these two values. So I do hope you found that video on capacitors networks, that's capacitors in series and parallel, useful. Okay, make sure you don't make the mistake of confusing the formulae with the ones for resistors. And secondly, don't forget that capacitors in series, the formula gives you 1 over the total capacitance. So when you get your answer, it'll be way too big and you need to reciprocal the number that's on your screen. Anyway, I'm going to be making another video soon, and I look forward to seeing you then.